Hello, science enthusiasts, and welcome back to the channel. Today we're diving headfirst into one of the most mind-bending, counterintuitive, and downright weird concepts in all of physics: quantum entanglement. Albert Einstein famously called it spooky action at a distance, and honestly, he wasn't wrong. But what is it really? Is it faster than light communication? Is it some kind of cosmic telepathy between particles? Let's unravel this mystery together. To start, let's imagine something simple. Picture two coins, but these aren't ordinary coins. They're special quantum coins. We link them together through a process, and then we put each coin into a separate, sealed box. We give one box to Alice and send her to the moon, while Bob stays here on Earth with the other box. Before they open their boxes, neither Alice nor Bob knows if their coin is heads or tails. It's in a state of pure possibility, a superposition of both. But here's the magic. The moment Alice opens her box and sees a heads, she instantly knows, with 100% certainty, that Bob's coin is tails, and vice versa. It doesn't matter if Bob is across the room or across the galaxy. The outcome of one measurement instantly influences the other. This inseparable connection between the two coins is the essence of quantum entanglement. Now, let's replace our magic coins with real subatomic particles, like electrons. Electrons have a property called spin, which, for our purposes, we can think of as being either spin up or spin down, our new heads or tails. If we entangle two electrons, their spins become linked. They exist in a shared state where their individual spins are undefined until one is measured. If we prepare them so their total spin is zero, and then we separate them by a vast distance, the moment we measure one electron and find its spin up, we know its entangled partner, wherever it is, must instantly become spin down. This isn't a guess. It's a certainty dictated by the laws of quantum mechanics. This is where the spooky part comes in. How does the second particle know the first one was measured? This apparent instantaneous correlation across vast distances seems to violate one of the most fundamental rules of the universe, that nothing, not even information, can travel faster than the speed of light. This is the very paradox that made Einstein so uncomfortable. He, along with physicists Boris Podolsky and Nathan Rosen, proposed that maybe the particles weren't communicating at all. They argued that maybe the outcome was predetermined from the moment the particles were entangled. They called this idea hidden variables. Think of it like this. Imagine you have a pair of gloves. You put one glove in each of two boxes without looking, and then you mail them to opposite ends of the earth. When your friend opens their box and finds a right-handed glove, they instantly know you have the left-handed one. There's no spooky action here. The information which glove was which was hidden in the boxes all along. Einstein believed quantum entanglement worked the same way. The particles, he thought, were like the gloves, carrying hidden instructions from the start. For decades, this was a philosophical debate. Was it spooky action, or was it hidden variables? Then, in the 1960s, a brilliant physicist named John Stuart Bell came along. He devised a mathematical theorem, now known as Bell's theorem, that could actually put this to the test. Bell's theorem essentially said, if the hidden variables theory is correct, then the correlations between measurements of entangled particles will always stay below a certain statistical limit. However, if quantum mechanics is correct and the spooky action is real, the correlations will exceed that limit. What followed were decades of increasingly precise experiments designed to test Bell's theorem. Scientists created and separated entangled particles, measuring their properties over and over again. And the results have been overwhelmingly clear, time and time again. The universe is in fact spooky. The statistical correlations consistently exceed the limit set by hidden variables. This means that the properties of the particles are not predetermined. The universe is not like a pair of gloves in boxes. The weirdness is real. The particle states truly are undecided until the moment of measurement, and their connection is genuinely instantaneous. So, if this spooky action is real, does it mean we can send messages faster than light? Imagine Alice on the moon and Bob on Earth, trying to use entangled electrons to communicate. Alice can measure her electron, and she finds it's either spin up or spin down, but she has no control over the outcome. It's completely random, like a coin flip. When she measures spin up, she knows Bob's is spin down. But this doesn't transmit any useful information to Bob. Bob also measures his electron and gets a random result. He has no way of knowing that Alice has even made a measurement, let alone what her result was. They could only confirm the correlation after the fact, by comparing their measurement logs, which would require communicating through conventional light-speed limited channels, like a phone call or an email. So, while the correlation is instantaneous, it can be used to send a Morse code message or stream a movie faster than light. The universe, it seems, has a clever way of protecting its speed limit. While entanglement might not give us Star Trek-style communicators, it is the cornerstone of revolutionary new technologies. Quantum computing is perhaps the most famous. A classical computer uses bits, which are either 0 or 1. A quantum computer uses qubits, which can be 0, 1, or both at the same time thanks to superposition. By entangling these qubits, a quantum computer can perform a massive number of calculations simultaneously. This could allow us to solve problems that are currently impossible for even the most powerful supercomputers, like designing new medicines, creating novel materials, and breaking complex encryption codes. Speaking of encryption, entanglement is also powering the future of secure communication. Quantum cryptography allows two parties to create an unbreakable encryption key. If an eavesdropper tries to intercept and measure the entangled particles being used to create the key, the very act of measurement disturbs the quantum state. This disturbance instantly alerts the intended recipients that their communication has been compromised. It's like having a security system built into the very fabric of physics. Beyond technology, entanglement forces us to reconsider the very nature of reality. It challenges our classical intuition about space, time, and causality. It suggests that on a fundamental level, the universe is not made of tiny, separate, independent things. Instead, it might be a deeply interconnected web, where parts of it can be linked in ways that defy our everyday experience of separation and distance. The two entangled electrons, no matter how far apart, are not two separate systems. They are, in a profound sense, a single unified system described by one wave function. Perhaps what we perceive as distance is just an illusion of our macroscopic world. Some physicists even speculate that space-time itself might emerge from a deeper level of quantum entanglement, like a hologram projected from a more fundamental reality. This is the frontier of modern physics, where we are still very much exploring. Quantum entanglement isn't just a quirky footnote in a textbook. It's a gateway to understanding the deepest secrets of the cosmos. It shows us that reality is far richer, stranger, and more interconnected than we ever could have imagined. What started as a spooky puzzle for Einstein has become a fundamental tool that is shaping the future of technology and our understanding of everything. So, what is quantum entanglement? It's a fundamental non-local connection between particles. It's not faster than light communication, but a perfect, instantaneous correlation. It adds the engine for the next technological revolution and a profound philosophical puzzle that hints at the true interconnected nature of our universe. It's one of the most beautiful and mysterious phenomena we've ever discovered. Thank you so much for joining me on this journey into the quantum realm. If you enjoyed this and want to explore more mind-bending science, be sure to hit that like button and subscribe to the channel. Let me know in the comments what other cosmic mysteries you'd like us to tackle next. Until then, stay curious.